All right, so good morning, happy Monday. It is wonderful to see everyone here today. It is my pleasure to welcome you this morning for our short course on hybrid space-ground observatories, revolutionizing the search for Earth-like exoplanets. This short course is part of a study program that we've been working with the fantastic Ahmed, John, and Stuart for over a year now. We are so excited to welcome everyone here to Pasadena, so thank you very much for taking the time to join us. My name is Harriet Brettel. I'm here as the Executive Director of the Keck Institute for Space Studies, and it's been such a pleasure to be working with the team on this short course and bringing everyone together today. Before we get into the talks, I want to take the opportunity to tell you a little bit more about the Keck Institute, or KISS as we affectionately know it. We are a think tank that is based here at Caltech. We work to bring together scientists and engineers to develop innovative new space missions and technologies that can help shape the future of space exploration. And I think the topic that we're here to discuss today exemplifies that fantastically. So to introduce KISS in a little bit more detail, I am just going to show a very quick video.
The Keck Institute for Space Studies is Caltech's think-do tank for space exploration. We look at advanced out there concepts for how to observe the Earth, how to gaze into the heavens beyond, and then what are the technologies that enable us to explore and create the data sets of the future. KISS's mission is to revolutionize space studies. We seek far out concepts that have breakthrough potential and seed the teams and investigators behind those concepts.
It's a really passionate group of experts that we're bringing together who really see a positive, expansive future.
I think what makes KISS unique is the level of ambition of the ideas that are being discussed.
It takes crazy ideas and it funnels them and channels them into something that is actionable and yet truly futuristic.
That kind of far out thinking lays the ground for audacious missions of the future and audacious technologies. And that's what KISS seeks to enable, is to make what is presently impossible possible.
And ask Ahmed Solomon, one of our wonderful co-leads for this study, to introduce our first speaker. Over to you.
So, can you hear me? All right. Thank you, Harriet. What a beautiful day today. Finally, we are here together to work through this interesting study. So today, we will have 6 short courses that will lay the groundwork for our KISS study topic this week. These short courses will present what we have done so far and will cover all the key technical aspects. And we will also discuss the tall balls, unknown, open questions, and the challenges that will work on throughout the week. So I will have the honor of introducing the speakers. We have John, our first speaker for the first short course on the Hyper Observatory for Earth-like exoplanet conceptual breakthrough. So John, Dr. John Mather is a senior astrophysicist at NASA Goddard, the Space Flight Center, and as a NASA postdoc and later civil servant at Goddard, Mather conceived CUBE satellite, Cosmic Background Explorer, and led the team beginning in 1974, leading to the launch in 1989 and Nobel Prize in 2006 in physics for the first precise measurement of the spectrum from the anisotropy of the cosmic microwave background radiation. As a senior project scientist for the James Webb Telescope, 1995 until 2023, John led the science teams and worked with the engineers and managers to make the world's most powerful telescopes. With Webster Cache, later on with Webster Cache, he proposed the Starsheet to work with the James Webb Telescope. And then since 2018, he has led the studies of NASA NIAC Hyper Observatory for Earth-like Exoplanet (HOE), which is the topic of this case study. Building teams, finding innovative solutions to technical challenges. So Mather received his PhD in physics at the University of Berkeley, 1974. So please join me in welcoming John Mather.
Well, okay. Good morning. Can you hear me in the back? Okay. Well, I'm so thrilled to be here, to be able to talk with a crowd of people who make this have a possibility of making an idea real. So it has been said in the beginning, what's the word? Well, we're going to have a lot of words, and maybe we'll have a telescope project that can see little planets like Earth orbiting around other stars. So how do we do this? Well, I want to tell you some of the stories. So here are some of our colleagues. Many more people have been thinking about this, and Eliad will tell you some of the work that we did before, especially on orbits. But anyway, this is just the beginning. There we go. Okay, very good. So here is Webster Cash. He came to my office in, I think, 2007, and he said, can we fly a starshade with the James Webb Space Telescope? Which, anyway, the answer was no, but we tried. So we wrote a proposal, we sent it in. It was hopeless at the time because the telescope was not, telescope itself looked plenty hard enough, so we're certainly not going to add a starshade to it. And it was hard, as you know. It took us a long time after that to get it up. But at any rate, here he is. He published a paper in 2006 about what you would do with a starshade. And he had already basically solved the math problem of how you should shape them. Many more people have improved the math since then, so we do know what shape to make the starshades. Anyway, this is in way of thanks to Webb. So this is our current idea. Because it's there because after working with Webb for a long time, I thought, are you sure the telescope has to be in space? And at the time, the answer was yes, because there were telescopes on the ground, but not big enough. But now we have a telescope on the ground that is coming, and we have two more that could be coming that are big enough. So what is this for? Well, can you cast a shadow of the star onto the moving observatory long enough to take a picture? And the answer is yes. So we solved the problem, cast a shadow. So there's the example orbit. It's a long ellipse, and we know how to do this. Basically, you have to match, the observatory is going at a certain velocity as the Earth spins. You have to make the orbital velocity match that. So it tells you 4 out of the 6 numbers that it takes to describe an orbit. And you still have a choice of how far out it is and what's the radial velocity, but that tells you the orbit. So a very long ellipse. So now you know what to do, you know where to put it, but then you say, but gosh, the observatory is accelerating. You can't just put the thing there, you have to keep pushing on it during the observation. So also, when you want to look at another star to see a planet around another one, or you want to do it again with another observatory, you have to have a different orbit. So the upshot is you need something to align the starshade during observation, and you need something else to change the orbit when you want to do that, which is a very large problem. Anyway, we worked on it, and I think you will see that we have answers enough to do this. And by the way, there's a picture on the right that says if you can do this, you can get a picture of a solar system 15 light years away in a 1-minute exposure. And that is shocking to people because we've known for so long how hard this problem is. And the reason that it's been hard in the past is telescopes are smaller and there's a lot of glare. If you don't block the glare of the bright star, you can't see anything. So no matter how smart your optics is, it's a hard problem. The sun is 10 billion times as bright as the Earth. And oh, by the way, why do you look for sun-like stars? Is because they're friendly. They last long enough for life to occur. It's the one example we have of known life. And smaller stars that might be easier are hostile. And bigger stars burn out real fast. So this is the kind of thing you have to look for, and so please, that's the job. So if you could do this, you could have basically the best observatory you could imagine for a lot of reasons. It's the most possible sensitivity you could have, the sharpest image you could get. You can see the farthest. There's a scaling law up there. How fast can you see something? The speed is proportional to the fourth power of the diameter of the telescope. Huge advantage of big telescope. The telescope we have in mind is 39 meters in diameter. 39 meters being about 6 times as big as the Webb or the potential Hab Worlds Observatory. So 6 to the 4th power is huge. You win if you can do this. You can also, after you get a picture, there's no doubt what you're looking at. You do not have a little fuzzy ball next to another little fuzzy ball. You have sharp images separated from each other. So that's pretty cool. Another advantage of this is you can definitely see through dust clouds. A lot of solar systems have dust clouds in them, quite bright, especially if they're young and have a lot of debris from asteroids and comets. So this is the right thing to have if you can do it, for many scientific reasons. Then we also said, well, everybody told me when we started, well, you can't see molecules in another atmosphere because Earth's atmosphere will absorb all those wavelengths. Well, the answer is no, that's not right. It does absorb, but not all of it, and you can still see quite well enough to tell if another planet is like Earth. Does it have oxygen and water in abundance? So, pretty cool. So, this is an example of measurements that were made already, and for some reason that picture looks very blurry to me. But at any rate, this is a measurement of Earth's radiation as seen by reflection off the moon. So we know what the Earth would look like, and it has spectral features due to ozone, water, oxygen, and even something called a vegetation red edge, which is the result of the color of chlorophyll. So if you could do this, you would say, oh, that's pretty interesting, isn't it? You might not be able to prove it was alive, but it would be really tempting. So we synthesized some spectra, and this is what one version of it is. See, the blue curve is another Earth, and you see the little ripples in the curve due to oxygen and water, and I think they'd be pretty convincing. And a startling result is that this planet, even at this distance, is brighter than the background sky. See, the red curve shows how bright is the sky, and it's bright, but not as bright as the planet. So this is not the assumptions people are used to thinking about. People are used to thinking, well, the planet's hopelessly faint and you can't see it. No, it's not true. So it also means you can see planets farther away with this method. So the upper curve shows hypothetical large planets warm, and they're very bright and easy to see. They will be fun. So why do you want to do it this way? There is a picture on the right showing that the sky is bright at infrared wavelengths and faint at visible wavelengths. So we have adaptive optics that works pretty well with infrared. We do not have very good functioning adaptive optics at visible band, but we know what to do. And we have done it. So this basically says the wavelength range in green is the right way to use this big telescope, because the sky is dark and there's pretty low interference from the Earth's atmosphere. So, and by the way, if you want to do this part, just adaptive optics, we know what to do, and Elliot has already demonstrated that you can do this with the with the Keck Observatory. Got the sharpest images ever doing this method. So, how does it work? Well, you make the star shade appear to stop in front of the star, hold it in place with jets. Well, how do you know how hard the jets have to thrust? You use the telescope on the ground to see, are you aligned? You find an error signal, send that back up to the star shade, so you can hold it there with a servo loop. So that's just ordinary kind of servo loop. You need a laser beacon at the center of the star shade, so you have something to focus on. So because you've just now blocked the star. You have to keep it quite well aligned, otherwise this shadow isn't dark enough. Oh, and by the way, just in case you run out of fuel, you might launch some more. We do know how to do refueling or replacement of the propulsion system, and if you want unlimited life, that's what you do. So the telescope, what does it need? It needs to be the biggest you can get. The European one is the biggest, and we have a 30-meter and a 24-meter coming up too if the American teams manage to get enough money. We have something called single conjugate adoptive optics in the telescope, which is the simplest kind. Basically means focus on that artificial star and make it sharp. So we can do that. We know how to buy the parts for that. We want to have a thing called a coronagraph in the telescope, which is, but it doesn't have to be as good as what you would do if you were hunting for planets with just a naked telescope. The coronagraph in the telescope can block all the light that came from the star shade itself. And that's been a problem for previous versions of star shades because star shades have holes in them, light leaks around the edge, they have their own kind of brightness, they can reflect back light, so block the light that came from the star shade and from the star, and then you can win. Then in the telescope you need instrument package, and we're going to hear later in the week about what instrument packages we already could have and what we might want to change if we wanted to optimize them for this. And then a startling fact is the telescope is so large you can actually take a picture of the star shade with petals. You can see the individual petals in the image taken from the ground. So quite a different idea from what we've had to cope with smaller telescopes and star shades in space. So that gives us hope that this can solve all the problems. So why now? Well, when we started, we had a lot of harder problems, and now we've made a few conceptual breakthroughs. So in our most recent NIAC work, we've had various ways to make ultralight version of the star shade. Ultralight means you could possibly afford it. If it's extremely heavy, you're never going to manage to get the money or the rocket or the fuel or all the other stuff that it takes to push it around in space. It means you could possibly afford to do it. We found out that there's a thing called hot gas propulsion. People talked about cold gas propulsion to keep the alignment in place. Well, if you could get hydrogen and heat it up hot, you can get a very good performance. So it's not impossible, I put it that way. It's maybe harder than you need to have, but it's not impossible. And it solves the problem that if you had regular chemical jets, they can be bright. They could interfere with observations. You might have to turn them off while you're observing. And so that means pulses and shapes and vibrations, and so you don't want that. So this makes a change of the requirements, a change of the mechanical requirements. So then because of all these things, we can actually relax the tolerances. So the previous generations of starshade designs all came out with, we have to be almost perfect in the shape. And because you can't tell the difference, the telescope cannot tell the difference between light from the starshade and light from the sky. Because we have a different case, the telescope is so big you can really tell the difference. So that's technical ideas are better, and now the telescope is coming up real soon now. People that have been to see the thing on the ground in Chile tell me it's astonishing to look at. This is not just a picture, this is a real thing. So, how am I doing in my time? Okay, just a few words about the orbit. I mentioned what we have to do. We have to stop the relative motion at the chosen time. So I'm calling it astrostationary. When I tell people this is what we need to do, everyone immediately leaps to the thinking about the geostationary orbit. And then they say, and I think this is 100% of the people I've talked to. We all do that. But what we need is called astrostationary, and it's only momentary. But you can do this, as I explained right at the beginning. So what orbit is it? Well, it's a long ellipse. You need at least a 5-day period. Otherwise, it comes too close to the Earth and you'll hit. So don't do that. So a 5-day period, it means you can come around and do it again at 5 days later. So if you missed the observation, or if you think the planet has moved or changed, you want to see it again, you can just repeat 5 days later, or 10, or 15, or whatever. A larger number of days is also possible. Elliott discovered that you can also have multiple choices during each orbit. It's almost perfect, stopping in front of every day. There's an almost perfect event. There's one that would be perfect, and the others you could get to if you tried. So it means multiple observation opportunities each orbit. So, okay, I think I told you that part. But the short version of this is after you solve the problem of how to build the star shade, your next problem is you're going to run out of fuel as fast as you do, because you need it to change the orbit and you need it to stay aligned during an observation. So you're going to the engineering side of this spacecraft is highest possible performance from the propulsion system. So solar electric propulsion with the highest specific impulse, highest electrical power that you can manage. You can always do something with low performance systems, but if you want to get a lot of stars, then you need more. So if you were limited by money, you would just say, I'm going to do it once with chemical propulsion only, because that would be simple. But that's probably not the right plan. We should be ambitious, because our observatory concept is able to see as far or farther than anybody else. So more targeted stars are available. We just need to get to them. So how do you use it? Well, if you're orbiting around, you check on your orbit. You say, am I aiming to the right place? When you get to the right place, then you send commands to set up the closed loop control. So you stay aligned, and you do this by observing the position error from the ground. Then you take your pictures, and you say, I see planets over there and there and there. Then probably what we'll have is a multi-object spectrometer, which says, I'm going to take a picture of that pixel and that pixel and that pixel, because I've got 9 planets to look at. And so you set that up, and you take an exposure as long as you can afford. And then you say, okay, am I done? And do I need to come back here next orbit, or do I want to go on to the next target? So we say, decide and go on to the next. So that's the operations sequence that I'm picturing. Here's a star shade. It's a lot like what other people have worked on star shades, but just I'm mentioning here that the actual technical requirements are a little different. Of course, the star shade has to be about the right shape. It has to have the pointy petals. It has to be optimized for the wavelength that we have in mind. But we have enough capability that we can, well, anyway, it is possible to get much better performance than a small star shade would do. So we need to be able to, there have to be at least two layers, because there will be holes in the star shade with micrometeorite punctures. We have to have not too much reflection coming back from the Earth. You know, we're pretty far from Earth, but some Earth shine is going out there. We don't want that coming back and saying, oh, look what I saw, another Earth. We don't want that. We want to make sure the sun, which is shining on this thing, does not reflect much into our telescope. So it's got to be oriented and tilted so whatever the sun is lighting up we don't see it with the telescope. So there's a mechanical configuration requirement. But the upshot at the end is, please look for the lowest possible mass, and let's go from that. So Elliott will show us the results from our current study, and Christine Gregg has done some studies of another way to deploy it, basically by assembling small parts with a lot of little robots. And so we have lots of ways to think about this. And so we can do this. What did I do? So the telescope has to be big, and it has to have the instruments that I mentioned, have to cover their white wavelengths. In principle, if we can get adaptive optics to work at ultraviolet wavelengths, then we can do something that we'll probably never be able to do with a space telescope, because coronagraphs are just too hard for space telescopes at UV. Too many pieces, too much loss in the optics. But why is UV interesting? Ozone. ozone is the exact reason that we can't see out, and why we're protected from the sunshine. It's a huge sign of oxygen. So we would be interested in UV, and we could try. This is a hard technical thing, but it's not impossible. So I think I told you what we needed to do already. By the way, the optical performance that we need to get is not so you can block the starlight. It is so you can see the planets. You just need efficiency. Do not have to have a perfect image quality. You just need efficiency. So it should mean that we can do this. So we have three basic concepts that we've worked on in the past. The ones that you've seen the beautiful movies of are unfolding a structure which is very definite in shape, and it's just thrilling to watch that deployment. But when we try to make a big one, it's pretty darn heavy. And so we said we can't afford to do that, we have to find another way. So we've got that one. We can construct something in space, as Christine's NIAC has worked on, and then the one that we've been working on lately, an inflatable version. So what does the spacecraft have to do? Basically, ordinary things. Point things in the right direction, be able to orient things. And this is an interesting thing. We got this 100-meter diameter thing, and it's made of thin plastic. So keep those jets off the plastic, please. But aside from that, there's nothing very special about the spacecraft bus, I think. The propulsion system is the special hard part. So there's some constraints about how do you orient when can you look at the target? So basically you want the target to be overhead, you want the sun to be below the horizon. That's the ideal. So how close can you get to that? Well, the target can still be observed down out to about 45 degrees from zenith. When you get farther out, then the adaptive optics doesn't work much. So that's one constraint. But so that's basically the thing you have to manage. The sun has to be below the horizon enough, and the target has to be high enough in the sky. So there are two seasons during the year. It's either sunrise or sunset for this, and then you have all these geometrical considerations. But basically, except for the poles, the celestial poles, most of it's available. I don't know of any super interesting stars that are near the celestial poles, so I think we can reach the ones that people care about the most. So I think maybe we'll stop because there are so many more things we can talk about, but I'm looking forward to finding out what everybody else has to tell us. So time for a few questions? Okay, so questions?